In this problem, we have to find the second half-life, and the problem gave us the first half-life. And this is a thermomolecular reaction, and they gave us the rate. We don't have the formula from the textbook, but we can derive it using the first order differential equation. To do that, I have to multiply dt on both sides. And then I can divide both sides by concentration cube. Then you notice that dt's cancel out, and leaving you only or the concentration on the left side and dt and the constant on the right side. I can rewrite it as a to the negative third power dA. Oh, and also I'm gonna multiply by -1, and on the left side we expect positive, on the right side we expect negative. From here we're gonna integrate both sides of the equation, and the time lower limit we're gonna set that t equals 0, and just t will be the final. And the same applies to our left side, the lower limit to be initial concentration of A, and the upper limit to be just simply concentration of A. Then you can put F if you want as a subscript, but it's not required. We're gonna use the antiderivative formula. So what we do, the general rule is you add 1 to the exponent, and that result of exponent is found on the denominator. So to illustrate that, I need to add 1, and I can -2 on both sides. On the denominator, I'm sorry. So this is what we get. But since we have upper and lower limit, we have to evaluate this accordingly. Actually, I'll put F here just so that you don't get confused with our general A here. Alright, so when I plug this in, I'm supposed to get 1 over minus, and you have another minus because of that minus in front of 2, 1 over 2a to the initial, and you have to square that. And then you have -k. Okay, k is a constant which you can just pull it outside our integration sign, and it's when you have integral something like this, it just becomes t. Okay, t plus c here. But when we have a upper and lower limit, we do not need that c. In other words, like it just becomes t0. You substitute t, and then you minus and substitute 0, just become t. So on the right side I get negative k t. I will also say tf. Okay, so I have the general equation. I will just trim it by multiplying -1 on both sides. Just so that I get the positive tf. Also, I'm gonna divide it both sides by k. Okay, on both sides. So in the end, I get tf equal, okay, now this will be positive, 1 over 2 concentration of vinyl squared minus, don't forget k, I just divided it, so one over 2k initial. Okay, this is the general formula of our thermomolecular reaction. But since our problem involves half-life, okay, you have to remember that at half-life the concentration is half of the original. What that means is I can simply substitute this in our final, and instead of writing tf, I can make it 1/2 to indicate that this is the formula for the half-life. So I have t-half equal 1 over 2k 1/2 a initial, and you have to square that. Make sure you put the parentheses around. Okay, that 1/2 has to be included in the parentheses, minus 1 over 2k. You just copy it. Alright, this is a little bit tricky, so be careful. When you square both, this becomes 1/4, right? So let me write that down. So 1/2 squared is 1/4, and the concentration just becomes squared. Now 1/4 times 2, you get 1/2, right? And then it's a reciprocate, so 1 over 1/2 becomes 2. So I have 2 over k times a naught squared minus 1 over 2k a naught squared. Well, I want to make the same denominator, common denominator. So what I can do is I can multiply 2 on both sides. And what does that become? 4, right? So I have 4. And since we have common denominator, we can rewrite it as 2k, or divide by, well, that's divided, and on the top you just get 3. So that's our half-life equation for our thermomolecular reaction. Now we have to answer the question. The problem said the half-life, the time is 40 seconds. Okay, but we are interested in the second half-life. So let me illustrate that. When you have a original, you have 100% concentration, and then during half-life you have the half 50%, right? And during the second half-life you have 25%. Okay. When we want to find the second half-life, remember from our first equation, first half-life, that was the original, right? Here, our original now becomes, instead of that the real original, now it becomes the this becomes our original. Okay, and this becomes our final. Or I can, instead of saying original, maybe I should have said initial. Same thing, but I guess the initial is more proper term. So in this time frame from after 40 seconds until the concentration from our first half-life becomes another becomes halved, we have to substitute. In other words, since this is our original, I have to rewrite this as t. Okay, that's our original, and we do the same thing of applying this. Okay, this so 1/2. Again, I think I'm overemphasizing it. That's our initial in our second frame, so you have to square that because our equation tells us so. Okay, you have to square 1/2, you get 1/4. 1/4 times 2, you get 1/2, and that 3 over 1/2, you get 6. Okay, this is what you get. There are multiple ways you can try. One is you can divide this by that to find our second half-life. Or you can also apply the substitution method, meaning multiply this on both sides. Then you notice that this cancel out, and then divide both sides by 40. So we get 3 over 80, and you notice that this is same thing as that. Okay, 6 times 80 over 3, you can two times 80, you get 160 seconds. That's our second half-life, from 50% to 25% our concentration. So to answer, our second half-life is 160 seconds. I don't think 6 weeks are important. Maybe we can put 1.6 times 10 to the second. So that's our final answer.